Alright, in this video we look at some common parametric surfaces and we discuss the concept of the surface normal. Alright, so in general a vector valued function in two variables into one, two, three-dimensional space is a parametric surface. So where you have a formula for x as a function of uv, y as a function of uv, and z as a function of u and v. Okay, and one of the most common examples is something called the Monge parameterized surface. Okay, and this parameterization looks like the following: r of u comma v is equal to u comma v, and then f evaluated at uv, where we know that z is some sort of function of x and y. Okay, so as an example here of a general Monge parameterized surface, here's a general Monge parameterized surface, and a specific example of that could be, let's say that you have the function z is equal to f of xy, and that function of two variables is maybe x times y, for example. Then the Monge parameterized version of that surface is u comma v, and then x is equal to u and y is equal to v, so z is equal to uv. So what we are seeing here is that x is equal to u, y is equal to v, and z is equal to u times v. So where we have x and y and z as functions of u and v, that is what we are calling a parameterized surface. Okay, and specifically when x is equal to u and y is equal to v, and then z is equal to the function x for u for x, and y for v. This is an example of a Monge parameterized surface. Okay, and then if you can describe that u and v, which are called your parameters, there are two parameters in this case. If you specify what they are, okay, let's say that you want u to go from 0 to 1 and v to go from, say, 0 to 2, then you would have z equal to u times v, where u goes from 0 to 1, v goes from 0 to 2, and then z is given as a function of the different points in the uv plane, and u is equal to x in this case, and v is equal to y. So you would have a set of u values that go from 0 to 1, v, which is equal to y, goes to 0 to 2, and then you could lay out a grid of uv values and then plug in for different uv values. You would get the value of z at that value of uv. And then if you collect enough points together, you will get a surface. Okay, so that's what we are seeing over here. For example, when I try to create a Monge parameterized surface, u for x, v for y, u multiplied by v for z. Okay, so this is the Monge parameterized version, Monge surface of z is equal to x multiplied by y. Okay, once you have that formula, you can do a parametric plot 3D. You can plot this function r of u comma v, and instead of t, which is we've done a parametric plot in the past, t going from somewhere to somewhere, we now have two parameters that need to change. U and v need to go from whatever you would like to specify them to be. And when you plot this function, you get that example of a surface. Okay, and we can see here that if you were to get rid of the z, look at this thing from the top, you would see that x Here's the x-axis going from 0 to 1, y is going from 0 to 2, and then for those different grid points in the UV plane, you could then plug in to find a value of z. Okay, so this is a pretty straightforward vector valued function and two parameters right here for a surface. And in general, as I said, if you want to have any function z is equal to f of xy. So for example, if z was equal to cosine of xy, then you could come up with a parametric form of that surface u comma v, and the z entry would be cosine of uv. Okay, so there would be a parametric form of the surface cosine of x times y, and all we're doing here is essentially changing x to be u and y to be v, so it's just kind of a change in notation. But there is the example of this surface when the x or u goes from 0 to 1 and y goes from, or v goes from 0 to 2. Okay. More interesting things happen when we move to x, y, and z, in the general case here being functions of u and v. Okay, but before we get to those examples, I want to discuss the concept of a normal vector. Okay, so what we have here, let's stay focused. Let's focus for the time being. Focus on a Monge, who is a French mathematician, a Monge surface. Okay, and that Monge surface is going to look like a vector valued function. X is equal to u, y is equal to v, and then we have some function of u and v. Okay. If we take the partial derivative of this function with respect to u, what that means is that we take the derivative of each entry of the vector with respect to u. Okay. And so we would see here that the partial derivative of u with respect to u is 1. The partial derivative of v with respect to u is 0. And the partial of the function with respect to u is f subscripted with u. So this is what we mean by the derivative of the vector valued function, the partial derivative with respect to u. Okay. There's also a partial derivative of the vector valued function with respect to v, which would be 0, 1, partial derivative of f with respect to v. Okay. Now we can see here that these are two vectors that we've probably seen before in the past. Okay. If you were to take the cross product of these two vectors, what you'll find that you get is minus the partial derivative of f with respect to u, minus partial derivative of f with respect to v, and then you'll get 1. Okay, so you can check that for yourself. This cross here, this x, that means the cross product. And I will let you look back at a review of the cross product. Okay, the question is, what is the interpretation? How do you interpret this vector, RU cross RV? Okay, so in the past, we have seen where this cross product comes in. Here we have a surface z is equal to f of xy. We also have an interpretation of it now as a vector valued function or a parametric surface r of u comma v, f of u comma v. And at a certain point here, we know that r sub v is a vector that points in the y direction on this surface. Okay, so if y is equal to v and x is equal to u, here is the vector r sub v. Oh, I should have drawn that in pink, sorry. U is equal to x. I should have drawn this rv is a vector in pink. At this same point, RU is a vector that points in the U direction. So there's RU. And when you compute the cross product of those vectors, RU cross RV, that is a vector that is perpendicular to both RU and RV. And so we've seen that vector before, that is the normal vector to the tangent plane. Okay, and so we've seen this before. RU cross RV is what we call the normal vector. Okay, and there is also another vector that is in the exact 180 degree opposite direction. That would be RV cross RU, right? And that is just the negative of RU cross RV. These are vectors that are the same vector, just in 180 degree opposite directions. Okay, so if you have any sort of function, z is equal to f of xy, we can compute the partial derivative of r with respect to u, the partial of r with respect to v, right here, compute their cross product, and that cross product is a vector that is perpendicular to the surface. Okay, so we have an example shown here. Here is the function of two variables. Z is equal to f of xy. Okay, this is the Monge parameterization for it. R of u comma v is some function of the function f evaluated at u and v. So here we can see is the output. Here's our vector valued function u comma v, u times v. Here are the partial derivatives, partial with respect to u, partial with respect to v, and when you cross product them, right, we can see that we are getting the negative of the partial derivative of this function with respect to x, which is u, which will give us negative y, and y is equal to v, and then we get negative partial of the function with respect to x, which is equal partial with respect to y, which is equal to here's the partial derivative and the cross product. Okay, what we're seeing here is on this surface I'm showing what the cross product, that vector n, looks like. Okay, there are two vectors, one of them being the blue vector and one of them being the red arrows, and we can see that they're pointing at exactly 180 degrees opposite from each other. But at every point on this surface, there is the blue vectors which point perpendicular or normal to the surface. They are pointing at right angles to the surface. Okay, so you can almost see, right? You can see these little squares on the surface, and those squares kind of can represent the tangent planes, and these arrows point perpendicular to those little tangent planes. And then there is on the other side vectors, the red arrows are pointing exactly 180 degrees opposite of the blue arrows, but they are still all perpendicular to each other, to the surface, just pointing in 180 degree opposite. So this is going to be true for any function. Let's say that the function is cosine, cosine of x multiplied by y. Okay, then what we will find here, let me run this code, that here is your parameterized surface. You can compute the partial derivative with respect to u, partial with respect to v, compute their cross products, which takes a little bit of practice, but is not a hard computation, just be careful. Okay, and we have the vectors, blue pointing perpendicular to the surface, and then red being 180 degrees. Okay, so this normal vector is very important. It essentially is telling you what is the direction of the surface at every point. Okay, So both blue and red arrows tell you the direction of how the surface is pointing. If you were walking along the surface, you would be standing. If you could stand straight up on that surface, you would be the little arrows pointing, and your head would be pointing in the direction of the surface. Okay, assuming you could kind of be stuck to the surface like these little arrows are. Okay, so we might want to check, like here's the partial derivatives, compute the cross products. Okay, so we can check that over here now with maybe a slightly simpler looking surface. So let's try x squared multiplied by y. Okay, and let's run this code, and we can go over here and double check these computations. Okay, for the normal vector. We're doing surface integrals in this section and computing the surface parametrically, and the direction of the surface is going to be essentially the first step 0 for any problem. If you have a surface, your goal is going to be to write it as a parametric function and then to find RU cross RV, the normal vector to that surface. Okay. So here we have an example. R of u comma v is, let's see, u comma v, and then the function was x squared y, so our function is u squared v in the z entry. So we can see here the partial derivative r sub u, partial derivative with respect to u is 1, 0, 2 uv. So I took the partial derivative of this entry with respect to u, which is 2uv. R sub v should be 0, 1. Partial derivative with respect to v is u squared. Okay. And then I'll remind you about the cross product here. Ru cross producted with Rv means that we need to take the I entry, the j entry, the k entry, write these vectors 1, 0, 2uv, 0, 1 u squared. Okay, and we need to compute these determinants, these subdeterminants. So I'm going to look at this square for the I entry. So we'll get 0 times u squared minus 2u times 1, which is minus 2uv, which is why we are seeing the minus 2uv here. Okay, the j entry gets an artificial minus sign. Okay, and then we will focus on this term, this term, this term, and this term. So we'll get u squared for that term. 1 times u squared minus 2uv times 0. And then the last entry, the k entry, we're going to focus on these numbers, and it comes out to be 1. Okay, so what we're seeing is that the normal vector is minus 2uv minus u squared 1. Okay, in other words, the normal vector is minus 2xy minus y squared 1. Okay, and that was for the surface z is equal to f of xy is equal to x squared y. So as promised, this entry of the vector is minus the partial derivative of the function with respect to x. The partial with respect to x is 2xy, minus sign. The partial derivative of f with respect to y is x squared, but there's a minus sign. And that's what was supposed to show up here, and the z entry of the normal vector was supposed to be equal to 1. Okay, so that ends the computations behind the normal vector to a Monge parametrized surface, and these normal vectors are essentially telling us the direction of the surface, and that will be fundamentally important for computing surface integrals.